All right, we're trying to determine the apparent weight of the astronaut in a rocket ship that is taking off. So now listen, what we're looking for is basically what kind of force is it? It's a normal force, okay? So we're looking for a normal force when what we have upward is, we're going to just call it the normal force, and we have mg acting downward, right? It's our free body diagram. This is for the astronaut. So how are we going to figure out what the normal force is? Well, this is pretty easy. This is going to reduce to, anybody?
Zero.
The elevator equation. All right, look. We got net force is equal to the mass of the astronaut, times the acceleration. Net force is also, this is true because it's always true, then the net force is equal to normal force in the positive direction, mg in the negative direction. We're going to get n minus mg is equal to ma, and then n is equal to m times g plus a, or m times g plus m times a, or m times the quantity g plus a. And as you guys came up with eventually, this is in fact the elevator equation. Now all we need to know is the acceleration, which is, they give us as, they don't give us the acceleration. What are we going to have to do? We're going to have to use kinematics, all right? This is what I was saying. All the stuff we're doing, that's what I was talking about the test, what's it on? It's really about everything that we've had all year. Because the kinematics is just learning the way and the relationships among all these quantities, the language of motion. Now we're talking about the why. What's happening, what's making these accelerations happen. So acceleration is the bridge between kinematics and Newton's laws, kinematics and dynamics. Now, projectile motion, time was the bridge, okay? But that's a different place, okay? You can't get across the James River on the Woodrow Wilson Bridge. It's a different bridge, different river. It's like a geography joke. Okay, all right, so now we need to figure out what the acceleration is, and we're going to use kinematics to do that. I already heard somebody mention VOTAT, but let's just run through the process and see what we have and how we're going to determine the acceleration. Still good. All right. All right. So now we have, I know we have V naught, it takes off from rest, I would assume. V naught is equal to 0. And I know it gives us a final velocity of, what's that? 45 meters per second. And we have a time, right? 15 seconds. All right, this looks pretty easy. Acceleration, we don't know. We want to know it. Looks to me like it's going to be 3 meters per second squared. Well, let's check it out. So we have VOTAT. V is equal to V naught plus AT. V naught is equal to 0. So acceleration is just going to be equal to velocity divided by time. It's actually delta V, right? Because we subtracted this, but it's 0. V is 45 meters per second. T is 3 seconds. 15 seconds. I already did the 3 in my head. 15 seconds. Meters per second divided by seconds. Multiply, right? Invert and multiply. It's, no, it's divided. Meters per second squared. 3 meters per second squared. All right, so that's our acceleration. What are we going to do with that? Plug it into what? Elevator equation. Now, if we were purists, what would we do? And you know that I am. We could just we could replace that expression V over A, right? Okay, instead of doing a calculation, we put it all into the same calculation, so we don't have to round because that would reduce our accuracy. All right, so N is equal to M times the quantity G plus V over T, as given. It's easy because it's simple. It comes out real clean. We could just have used 3. But normal force is equal to, what was it, 47 kilograms times 9.57. Easy, fellas. All right, 57 kilograms times 9.8 meters per second squared plus V, 45 meters per second over 15 seconds. I know it's 3. All right, that turns out to be equal to what? 13. Say again? 729.6 sounds like 730 newtons to me. That's the normal force. The normal force is the apparent weight that we were looking for. Apparently.